Great. So we're very happy to have Igor Broeckel give us a talk about moduli stabilization and statistics of the landscape. So, away.
Okay. Hi everyone, thank you. I would like to start first by thanking the organizers for giving me the chance to talk today. And I will speak about modular stabilization and the statistics of SUSY breaking in the landscape. And this work is based on a collaboration with Kähler, Anshuman Maharana, Kajal Singh, and Kuva Sinha. And the main motivation for this work was basically to emphasize the importance of modular stabilization, Kähler modular stabilization, in the context of the statistics of SUSY breaking. And indeed, in our work, we find that different ways of stabilizing Kähler moduli lead to a different functional behavior of the distribution of SUSY breaking scales in the landscape. As a spoiler. Okay, so I will start by reviewing the statistical approach in this program, and then I will highlight the importance of Kähler modular stabilization. Then I will shortly review the different stabilization mechanisms that we study, which is LBS, KKLT, and the purely perturbative stabilization. Then I will summarize our results, so the SUSY breaking statistics, and then I will shortly mention some phenomenological implications in the conclusion. Okay. So we know that SUSY is a central idea in Finetuning and theory. It gives a nice solution to the Kähler problem. It provides dynamical candidates, so it's just a very crucial concept in modern physics. But so far we haven't seen SUSY in LHC. So one question is whether string theory can give some sort of guidance in the search of SUSY. So is it possible to give a preferred energy scale where we might be able to find SUSY coming from stringy arguments? And so the idea is not to study a specific vacuum, but study the landscape in a statistical way in order to find this kind of preferred energy scale. So why can we do that? We know the landscape is very large. There is no preferred vacuum, but we know that there are many vacua that at least roughly match the standard model. So the statistical analysis should be justified in this case. And first studies in this direction were published in the beginning of the 2000s, most prominently by Denef and Douglas. And these studies found a preference for high energy, high scale SUSY due to a uniform distribution of the SUSY breaking scale. However, these studies mainly focused on the distribution of the dilaton and the complex structure F terms, and they neglected the Kähler moduli F terms. The reason for that is that Kähler moduli are flat directions at the tree level, and they get stabilized only at higher order corrections. So it was believed that the dynamics that lead to a stabilization of the Kähler moduli would give rise only to subleading corrections to the leading order picture coming from the dilaton and the complex structure F terms. In the literature, you can also find expectations to find a logarithmic behavior of the SUSY breaking scale, where these arguments are mostly based on dynamical SUSY breaking arguments. So, as I said, in the literature, we can find arguments for power law behavior and for logarithmic scaling. But what is the origin? So it was not quite clear yet what the underlying reason for these kind of laws is, which we try to answer in our work. Okay, so let me start by shortly summarize the results of the seminal work of Denef and Douglas. So we start with the tree-level Kähler potential of this form. We add the superpotential at the tree level of this form. Then we combine both expressions and use the standard expression for the supergravity scalar potential in order to compute the tree-level scalar potential, which you can see here, where the gravitino mass is given by this formula. And now, as is already mentioned before, in the work of Denef and Douglas, the Kähler moduli F terms have been neglected, which you can see here. This is a crucial step. So, as I said, it was believed that they would lead only to a small subleading correction to the leading order picture coming from the dilaton and the complex structure F terms. So it was assumed that the distribution of the SUSY breaking vacua was taking this form here. So it depends only on the F terms of the dilaton, of the complex structure, and the depth of the potential, where rho is the density function. Now, Douglas introduced a crucial assumption where the distribution of the SUSY breaking scale and the distribution of the cosmological constant are in fact independent. And this assumption relied on the existence of several hidden sectors. So by assuming this, it's possible to basically neglect the dependence on lambda in the density function. So by including also the constraint of a vanishing cosmological constant, and by assuming a uniform distribution of the axial dilaton in the complex structure, it is straightforward to reformulate this distribution in this form. Where, again, by assuming a uniform distribution for the axial dilaton and the complex structure, it was assumed that the distribution function rho is in fact independent of the gravitino mass. So this beta coefficient here was 0 in the result of Douglas. But we will see that if we properly stabilize the Kähler moduli, this beta is in fact not always 0. It is 0 for KKLT, but for LBS it will be -2, and a different number for a purely perturbatively stabilized scenario. But let us first talk about why Kähler modular stabilization is actually important in this case. So if we remember that the superpotential at tree level is does not depend on the Kähler moduli, then we can rewrite the tree level scalar potential in this form. And by using the Noscale relation, which basically states that this expression here is equal to 3, we can cancel out this third term here. So we are left only with the first 2 terms, which can be rewritten in this form here. So we immediately see that any vacuum where diw is not equal to 0 is unstable, since it gives a rise to a runaway behavior for the volume mode. Hence, if we want to achieve a stable solution, we require Fs and Fu to be equal to 0, or at least to be suppressed with respect to the F terms coming from the Kähler moduli. Another important observation is that at tree level, the gravitino mass is set by the F terms of the T moduli, since the Noscale relation implies this relation here between the F terms of the T moduli and the gravitino mass. Another important insight is that soft terms are of order of the gravitino mass only for matter located on the 7 branes, not for the 3 branes. So for instance, Gaussian masses for the 3s are set by the dilaton F term, and which is non-zero due to sublink corrections only beyond tree level. So in order to determine the value of the dilaton F term, one needs to stabilize the Kähler moduli. So we can conclude, in order to have a consistent study of SUSY statistics, we need to stabilize the Kähler moduli first. And indeed, the SUSY statistics will be driven by the Kähler moduli primarily. So let us review the stabilization mechanisms that we studied. And we start with KKLT. So KKLT is a purely non-perturbative stabilization. We start with the Kähler potential of this form, so the tree-level Kähler potential, and then we add non-perturbative effects to the superpotential of this form here, where T is the Kähler modulus given here, and A, or more precisely, little a inside the expression of A, is a parameter that determines the nature of the non-perturbative effect that we use. So we can take the tree-level Kähler potential and this superpotential and compute the scalar potential. After minimizing the scalar potential with respect to the axion and with respect to the modulus, we can obtain this relation, which is true at the minimum of the scalar potential. So we can use this relation in order to reformulate the expression for the gravitino mass, which holds at the minimum of the scalar potential, which you can see here in this box here. So this is the main formula of this slide. So note that in KKLT, the gravitino mass depends on G string, on this little n parameter, and the tree-level superpotential. Now, quite generally in KKLT, in order to be able to neglect stringy corrections to the effective action and perturbative corrections to the Kähler potential, one needs exponentially small W0s. So this implies that the scale of the gravitino mass in KKLT is mainly driven by the value of W0, which is not true for different stabilization mechanisms, as we will see. So, for instance, if we take a look on LBS, LBS is a scenario where we combine perturbative and non-perturbative mechanisms. So, we add alpha prime perturbative corrections to the Kähler potential here, plus the S-dependent and complex structure dependent terms that we've seen before. And we also add non-perturbative corrections to the superpotential of this form, where small as is the same as in the KKLT case. So it also determines the nature of the non-perturbative correction. So we can play the same game again. We can use the Kähler potential and this superpotential in order to compute this Kähler potential, and then minimizing the potential with respect to the axions and with respect to the moduli, which gives us these two relations here that are true at the minimum of the potential. Now, the main point about this relation here is basically this exponential function, which depends on 1 over G string, as you can see here. So if we use the volume in order to re-express the gravitino mass at the minimum of the potential, which you can see here, where C1 and C2 are basically numerical coefficients, then you can see that the gravitino mass depends only on G string and N. So there is no W0 dependence as in KKLT. And more importantly, we have an exponential dependence on 1 over G string. So we can conclude that the gravitino mass in LBS is mainly driven by a small value of G string, since we need a small value of G string in order to have large volumes, in order to have control over the field. Okay, so just a reminder, in KKLT, the gravitino mass is driven mainly by a small value of W0. In LBS, however, by a small value of G string. Yet another behavior we can observe in a purely perturbative stabilization mechanism. So it was shown that if the tree-level superpotential takes natural values, say in between 1 and 10, and in the absence of small blow-up cycles like in LBS, then the non-perturbative corrections are subleading with respect to the perturbative corrections. And you can see here the leading order perturbative corrections to the Kähler potential. Now, the functions B and C are functions of the complex structure, and they are known explicitly only for simple toroidal orientifolds, but are expected quite generally to be of order 1 to 10. Now, in this case, we can also play the same game again. We can take the full Kähler potential and the superpotential, compute the scalar potential with the supergravity formula, and minimize the result with respect to the axions and with respect to the moduli. Then we obtain this relation, which holds true at the minimum of the potential. Now, we can use this expression again to rewrite the gravitino mass at the minimum of the potential for the purely perturbative case, which is given by this expression here, where lambda is just a numerical prefactor. Now, in this case, the gravitino mass depends on W0, G string, and this function C. Now, in the case of a purely perturbative stabilization, we use G string corrections and alpha prime corrections. The G string expansion is mainly controlled by G string, and the alpha prime expansion is controlled by 1 over volume cubed. So in order to have control over these expansions, we need a small G string and a large volume. So if we go back to this expression here, we see that we can achieve both conditions only if we tune the function C to be very large. So we can conclude that the gravitino mass in the purely perturbative stabilization is mainly driven by the function C. Okay? So now we have seen that the gravitino mass in all the three stabilization mechanisms is mainly determined by W0, G string, this little parameter n, and the function C. Now what we would like to do is to determine the scaling of these fundamental parameters in the landscape in order to be able to write down the scaling of the gravitino mass in all three stabilization mechanisms within the landscape. So the literature, there are many arguments in the literature for a uniform distribution of W0 squared as a complex variable in the complex plane. So we assume for the tree-level superpotential this form of a distribution. The distribution for G string was checked by us explicitly for rigid color BLs, and we've seen a uniform distribution. And it was recently shown by this group here that this uniform distribution seems to hold also for more general color BLs and more general geometries. So we assume a uniform distribution for a G string. The distribution for the rank of the condensing gauge group is still very poorly understood, but we expect the number of states n to decrease if we increase the small parameter n, since the tadpole cancellation is more difficult to satisfy in these regimes. So we assume this, let's say, phenomenological kind of scaling where r is a positive integer or positive number. The function c, as I said before, is a function of the complex structure. So we expect its values to be between 1 and 10. So since we need very large values of c, this seems to be a very fine-tuned situation. So we assume a similar scaling behavior as in the case for n with a positive k. So we can use the information that we have about these fundamental parameters here in order to compute the scaling behavior of the gravitino mass in LDS, KKLT, and in the purely perturbative stabilization mechanism. So let's start with LDS. If we take the expression for the gravitino mass in LDS that we've seen before and just take its variation and then include all the information about these underlying parameters that we just seen, we obtain this result here. And it is interesting to see that the details about the distribution of this little n parameter is basically encoded in this last term, since here we can see the dependence on R. But it is interesting that the leading order result is actually independent of the concrete details of the distribution, since this term will always contribute only a subleading logarithmic correction to the leading order result, which is given by this prefactor here. So in order to make contact with the language of the and Douglas, we can extract from this expression the density function rho for the LDS case, and we see indeed that the density function does depend on the gravitino mass with an exponent -2. And this density function leads to a logarithmic scaling the gravitino mass. So we know that in LDS models, the soft masses scale with the gravitino mass with power 1 over p, where p is a model-dependent parameter. So from that we can conclude that LDS vacua feature a logarithmic distribution of soft terms in the landscape. We observe a different behavior for KKLT models. So we can play the same game. We take the expression for the gravitino mass that we derived in KKLT, take its variation, and then include the information that we have about the underlying parameters. Then we obtain this expression here. And again, we can see here that the details on the distribution of n is not really important in this expression, since the second term is suppressed by this prefactor. So the leading order result is given by this first term here. So we can again extract the density function for KKLT, but in KKLT we indeed see that the density function does not depend on the gravitino mass. So we can, so for KKLT, we agree with the results of Denef and Douglas, and we produce a constant density function. However, a constant density function results in a power law distribution. So in KKLT, we know that the gravitino mass is proportional to the soft masses, from which we can conclude that KKLT vacua feature power law distributions of soft terms. Yet a slightly different behavior we can see in purely perturbatively stabilized models. So here we can again play the same game. We write down the expression of the gravitino mass in the purely perturbative stabilized model and obtain this expression here. One can argue that the field theory requires the exponent coefficient k to be larger than 1, which leads to a domination of this first term here. So after rewriting C in terms of the gravitino mass, we can obtain this expression for the density function of in the perturbative case. And we can see that it is qualitatively very similar to KKLT and reproduces KKLT for k equals to 7. So also for the purely perturbatively stabilised vacua, we observe a power law distribution of soft terms. Okay. So we have seen for all three different stabilization mechanisms a draw towards high-scale supersymmetry breaking. So a strong draw in KKLT and purely perturbatively stabilized models, and a slightly milder draw in LBS, but nonetheless, in all three cases, a draw towards high scales. So one might argue that this might be the reason why we haven't found any SUSY at LHC yet. We know that the problem of high-scale supersymmetry is that we need to introduce fine-tuning for the Higgs mass. And one way to quantify fine-tuning is to introduce the famous Barbieri-Giudice measure, which is given in this expression here, where mz is the Z boson mass and p are the parameters of your model. So this expression basically quantifies the amount of fine-tuning of your model. And you can see that even for TeV scale superpartners, you still get a fine-tuning of about 10%, which means that fine-tuning in general is a general issue. So in order to tackle this problem, one might introduce further ingredients in our analysis. So for instance, one could introduce fine-tuning penalties like anthropic arguments, which would set a bound on the mass of the Z boson, which in turn would set a bound on the scale of superpartners. Or one might introduce cosmological constraints, like the cosmological moduli problem. But these are considerations that we will leave for further studies. Okay, now let me conclude. We have stressed that Kähler modular stabilization is a critical requirement for a proper treatment of the statistics of supersymmetry breaking. Now, we have shown that different no-scale breaking effects used to fix the Kähler moduli lead to a different dependence in the gravitino mass on the flux-dependent macroscopic parameters, such as W0, G string, and the function C, and the small parameter n. We have shown that in LBS models, the distribution of the gravitino mass and the soft terms is logarithmic, whereas in KKLT and perturbatively stabilized models, the distribution is power law. Now, in order to determining which distribution is more representative of the structure of the flux landscape translates basically into the question which vacua are more frequent, LBS or KKLT. And since LBS models needs less fine-tuning, so it admits a larger parameter space, one might argue that LBS models might be favored. But in order to give a definite answer on this, one requires some more detailed studies of numerical nature. Okay. Thank you.
Great. Thanks a lot, Igor, for the very nice talk. Let us clap. It seems like Menki has a question.
Hello. Thanks a lot for the nice talk. So I wanted to ask you about some basic assumptions that you're making. Is it correct to understand that you're assuming that the G string and W0 are not correlated when you're driving the distribution from for the KKLT and LVS? It seems like you're assuming that G string and W0 are basically independent.
Yes.
Okay.
Yes.
Then the following question is that now we have some strong evidence that when W0 is small, exponentially small, then G string is parametrically logarithmic log in W0. So if I plug that correlation into your formula for the distribution, it looks like LVS and KKLT are featuring almost similar distribution. Then like if you take that kind of correlation into account, would you say that KKLT also features logarithmic distribution? Hence, there is no huge difference in the distribution of the gravitino mass?
So you're saying if you're pushing the tree-level Kähler potential to very small values, you also push the G string to smaller values.
Yes, that is at least what we have seen for most of the examples where W0 is small.
I'm not quite sure which work you are referring to, but
Manki, can I ask you, this is Sinha. Are you basically saying that for small W0, we should also take into account the correlation between W0 and G-string distributions? And if one way to do that, for KKLT would also obtain logarithmic distributions for the gravitino mass? Is that roughly what you're saying?
Yes. So what I have seen from the formulas that Igor has presented is that the crucial difference between LVS and KKLT is that in LVS, so basically the distribution is e to the minus 1 over some g string, and in KKLT distribution is like W0 divided by log of W0 3 half. And if you take the correlation between G string and W0 into account when W0 is small, those two parametric scaling is roughly similar, except for some tiny numerical factors. Then I don't expect that there is going to be a huge difference in the distribution for the gravitino mass in the end.
I think that's a very interesting thing to look into. This is something that Douglas and Denef, did not, however, they were not very, they took W0 distributions to be roughly uniform.
Oh yeah, but they didn't study the correlation between W0 and G string, right?
Yes, okay.
They only studied the distribution of W0 independently.
True. Mm-hmm. Very nice. Mm-hmm.
Cody, you have a question?
Hi, Igor. Thanks for the very nice talk. It seems like built into this study of the distribution of SUSY breaking scales was you set the F terms in the complex structure sector to be 0 initially, right?
yeah, of the F term of the kilomoduli.
And so even with that, you found that with most moduli stabilization schemes, there was a preference for high SUSY breaking scales.
Yes.
And so if you were to include this vacua with large F terms in the complex structure side, this seems like an even harsher problem, right? So you have larger SUSY breaking scales just coming from complex structure. So in this sense, it makes LVS seem even more special because of all these modular stabilization schemes. This is the only one that's giving you this logarithmic distribution. Is that correct?
Well, the reason why basically Denef and Douglas found a preference for high scale SUSY and like a power law distribution is basically that the F terms of the dilaton and the complex structure are also basically governed by the distribution of W0, which is the same for KKLT since the gravitino mass is governed by the distribution of W0. So this is, and since one assumes a uniform distribution of W0 in the complex plane, this leads basically to the same behavior in KKLT and the results of Denef and Douglas.
Got it. Okay. Awesome. Thank you.
Sure.
Great. Well, in lieu of time, maybe we should end and thank our two speakers again for their very nice talks.